This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Welcome to another episode of Design Safe Radio. Today we've got Jason DeJong from UC Davis. And if you're watching on YouTube, you can see the centrifuge virtually behind him anyway. Jason, it's good to see you.
Yeah, you too. Glad to be here.
So, just before we get into the questions for today, and since you've got the hardware behind you, can you give us a little bit of background of how you came to be at UC Davis and what is that big thing behind you?
Yeah, my story of coming to UC Davis is actually kind of a circular one in that I was an undergraduate student here back in the early 90s. And after finishing undergrad here, kind of made my way around to Atlanta, Georgia Tech for graduate school. Then a stint in Australia, actually as a postdoc, then at University of Massachusetts. Started my faculty career out there, and then they had a job opening, and you know, it's one in a million where you can actually go back and work at the same place you went to undergrad, let alone I actually grew up here. So
cool.
From that standpoint, it's been really cool. So I came back here in 2005. And then over the course of time, it's just become more and more involved in the centrifuge and Center for Geotechnical Modeling and everything that we're about. So it's been a fun journey, but it's been really nice to be here for the last 15 plus years. Time flies.
Wow.
So, crazy. Yeah. So anyways, so that's kind of the story. The centrifuge, this is the large one. We actually have two facilities, a 9-meter radius centrifuge and a 1-meter radius centrifuge. What you see behind me is the larger of those two. You can see kind of over off the one side, you can see kind of the center spindle, and from there measuring out to the end of it, which is kind of this big centrifuge bucket, is about 9 meters. And so it's really large device. The model containers that we put inside that have like physical models of whatever you want to simulate, whatever kind of natural hazard loading you're trying to understand, pop into the end of that bucket. And then as you spin, and as this thing rotates around, the faster and faster you spin, that entire bucket actually hinges up. And when it hinges up in that process, and this thing is, your model is basically vertical, spinning really, really fast around the centrifuge rotunda. And through that, you can simulate G level. So actually I have a little, this is slow motion, because otherwise we can't be in there, but this is this is my fun background. So you can see this thing rotating around the center spindle. That's the counterweight. And then you can see coming by here, it's going to knock my head in a second. Right there is the container on it, and it's like and it goes by. So the model is basically sitting level, as you can see, but you can imagine this thing not going, you know, a small fraction of a rotation per second. This thing will go up in excess of 1 rotation per second.
Whoa.
And at that point in time, it's flying, it's moving really fast. But on the end of that container, then while all that's happening, you have all the data acquisition, you have the model, you're simulating the earthquake and everything else. So it's a really cool piece of equipment. It's a huge toy, which gives us unique capabilities that arguably no other platform can give us. So it fills a very specific kind of niche in it.
Yeah.
So,
which is a great segue to our first question for the day. Thank you.
Yeah.
So for those who don't know or are unfamiliar with this type of work, can you kind of explain how engineers use centrifuges like this to research natural hazards like earthquakes?
Yeah, I think the term centrifuge is a physical device right? So this is a very large version of a centrifuge, and the very small versions back from high school biology or chemistry lab, and you spin a little vial and you see how the different solutions kind of separate out based off of their weight. It's all the same principle, and the principle is just generating a hypergravity platform. And that is, we are spinning this around, and as we spin faster and faster and faster, the gravitational field goes up. And so we obviously live at 1G, and on a device like this, and on a smaller device, and you can create G fields anywhere from 1G up to, let's say, 200G.
Oh, man.
And so
wow.
that's a huge amount.
Yeah.
We oftentimes aren't testing in those very, very high levels, but in this device behind me, for example, will often spin at, let's say, 50 G. And so you're spinning fast enough, so you're generating a 50 G gravitational field. And in that hypergravity field, you scale stresses and lengths appropriately, proportionally. So if we had let's say a 1 foot high model of a little embankment or a dam, and we're at 50 times, then we're actually simulating the stress profile from a 50-foot high dam, but it's only this big. And so that proportional scaling is amazing, because we can do things and we can simulate real world systems that we can't really do any other way.
And do the physical properties of things like steel and sand scale pretty well, or do you have some kind of filtering equations that kind of account for things that don't scale so well?
Yeah, yes and yes. Some things scale really well, and it's just a straightforward, like stress is very direct. It's just proportional to G, and that's it. There's other aspects in terms of modeling diffusion. A lot of times with earthquakes, we get these excess pore pressures and then the time rate of diffusion. In order to get that right, then you have to start scaling the pore fluid, and that can become a little more complicated.
Okay.
Or if you have structures, you can't just take, let's say, a steel structure and use steel on the centrifuge, because you have to scale not the absolute properties of the materials, but the properties of the members and their yield stress point and their failure point and some of these other things. And so it can get a little bit complicated. You usually can't match everything, but you can match a lot, and you have enough flexibility where you can choose, hey, I think these things are important. I'm going to scale those proportionally. And then through my analysis of the model and the results and the translation of that to the real world, to full scale, then I can use my equations and I can use some numerical simulations to kind of bridge that gap on some of the things that we can't nail down perfectly.
So if you're looking at how far a bridge piling deflects or something, you can look at the stress, the strain, the elastic and plastic deformation, but you may not care so much about the pore diffusion of the water underneath the water table.
You have a choice, right, of what you'd want to highlight. I think one of the great examples of this, actually that Bruce Cutter, one of the former directors, did, is the Bart Tube system. The Bart system is our underground transportation system in the Bay Area. And they were concerned about the tunnel that basically connects Oakland with San Francisco. And there's a Bart tube that lays across the bottom of the bay all the way, built 80 years ago, 90 years ago.
Oh, wow.
Or so. And they were really concerned, because that's full of air, obviously, with the subways going back and forth, that in an earthquake, that buoyancy could result in that buried tube potentially popping up. And if it popped up, then you would have cracking and infilling of water and everything else. And so Bart came and talked to Bruce, and they were working with Fugro, and everyone was kind of all tied together. He said, all right, let's model this thing. And we didn't try to model the exact Bart tube. We didn't try to model the exact subsurface conditions, but through some modeling, they said, these are the main mechanisms of how this thing could fail. Now let's build a model which is a little bit more simple, but will really reveal those mechanisms. We studied that. They did a few amazing tests. They took those results, and then working with numerical simulations, they arrived at the conclusion that, hey, good news, in fact, that tube as it currently exists is fine. It can handle the predicted earthquake loading, and you don't have to go out there and spend a lot of money doing a lot of fixes. So I feel like that's always kind of one of the great examples of where you can take a real world problem, distill out the mechanisms that you think will govern its failure, study those, and then go back to the real world system. But we didn't have to worry about, oh, they use rivets and all these types of things and putting a tube together. That's not relevant to the problem, so we can set those aside. So it's really neat when we have those opportunities, when we have people from industry or from the real world either coming with a specific problem or just coming with a problem that they've encountered many times, and then that can kind of drive some of the research that we do.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.